So hi everyone. So I thank the organizers for giving me this opportunity to talk about our work. So I will talk about Hilbert's space of de Sitter quantum gravity. This is the work we are doing with Tunir, Joy. No, sorry. Yeah. This is the work we are doing with Tunir, Joydeep, Victor, and Shubhrat. Tunir, Victor, and Shubhrat is here, and Joydeep was here. Joydeep is now at McGill. I will talk about the first part. Tunir will continue with the second part just after me. So let's start. So our universe is expanding, and we can model this universe as a late time de Sitter space. Now, what is the de Sitter space? Now, de Sitter space can be visualized as a hyperboloid, like it is like a sphere, but it is like first it is contracting, then again expanding. Like you can see like this for a d plus one dimensional de Sitter, you can like write the metric here with this cos hyperbolic t. You can see like at early times it was like first contracting, then again at late time it is expanding. So we are at the late time. Our universe is like, we can model is a late time de Sitter, and it has a positive cosmological constant. Here it is, yeah, this lambda is greater than 0. Now we want to write the wave function of this universe. Like now the wave functions, so these are like basically states, but these are written in the Schrodinger representation. When we deal with field theory, we don't like usually go to the Schrodinger representation, but in this case, it is very helpful for us. So this is just like in quantum mechanics, we make like wave functions. Now we make wave functionals, and these wave functionals are actually like functional of this these fields. Like here, this is some metric, and chi is like some scalar field, and these are at a given time slice. So at a given time slice, we can make these wave functionals as a functional of these field values on these slices. And just like in quantum mechanics, we find some like expectation value, we can here also find the correlation functions. These are like this, we mod psi square times this insertion and with the appropriate measure. So this is the Schrodinger representation. But when we are saying we are like doing gravity, that additionally imposes some constraints. Like these are like this Hamiltonian and momentum constraint. This Hamiltonian constraint is also called like Wheeler-DeWitt equation. And these are like this gauge invariance here. And this basically says like the physical state should not change under this gauge transformation kind of thing. So this H here, this Hamiltonian constraint, this is actually some time reparameterization invariance, and this HI is also like spatial diffeomorphism invariance. Like remember, like we are only dealing with some like constant time slices. So all these fields, all this metric, they're on this like constant time slices. Okay. Now so we can think like these constants are like some analog of Gauss law, like we have in EM theory, but obviously the gravity and any other gauge theory is like very fundamentally different. That we'll probably talk about, or Tunil will talk about it later. Okay. Now, what are these space of the valid wave functionals that satisfy these constraints? So one very simple example is this Hartle-Hawking state. So Hartle-Hawking, like in 1983, they proposed like this, you can do some path integral in Euclidean space to find the ground state. And these are like, this is the like usual prescription we do when you want to find some ground state of like field theory. We go to the Euclidean space and do a path integral with some boundary condition. And then you can get the ground state. And this ground state wave functional here, they obey this Hamiltonian momentum constraint. But what are the other states? So if we put just arbitrary insertions on top of this vacuum state, they will not necessarily make a quantum gravity invariant state. So what are the other states? So in this regard, Higuchi in 1991, he made a proposal. So he made this, he dealt with this de Sitter isometry charges. So isometry charges are like another version of this constraint. These are like integrated constraint, you can think, and they follow this de Sitter algebra. And so here, this is the same like this, earlier it was H psi, and now it is this charges, these de Sitter charges acting on this side and in ADS of flat space, it happens like they have some boundary, the charges give you some boundary value, and de Sitter, as you already saw, it is actually like a sphere, it has no boundary. So it should annihilate to 0. Now, so Higuchi made a very like heuristic proposal in this regard. He said, okay, take a like UFT state and and now average over this de Sitter group. This is by definition like a de Sitter group invariant state. So like if you can exponentiate one of the charges, so you can just see like this u prime psi is a psi. So this huge I actually just annihilates this psi. But why we should do a group average? What's the like fundamental thing behind that? That people did not know about that. So this is the thing, like group averaging is a very heuristic idea that he proposed. Yeah, it works, but we don't know, like there should be some more fundamental discussion from where it emerges. So we want to attack this problem, and we solved it with this with this work. And to solve this problem, we want to very like large volume limit. So you remember like this is like this finite time slices, and as you like go like up, this is the late time slices, and we go to a limit where this Ricci scalar and this all the potential terms of the Hamiltonian constant. So like these are like uniformly like very like less than like all over the slices, like uniformly they are like very less than this lambda, this cosmological constant. This is same as saying like the Cauchy slice volume here. This is like this here. This go large, and we are expanding Hamiltonian constants and momentum Hamiltonian constant here about this large volume. And to make it more manifest, we change our variable. Like Gij is like omega square gamma ij with det gamma 1. Also, this matter field it also has a scaling behavior like omega to the power delta O, and we specifically take large omega limit. What do we get after this? Yeah, so we get this solution. So this solution at large omega, it looks like e to the power is, which is a function of also g and chi, and some z, g and chi. Now this is like universal phase factor, and it contains the like integrals over local densities, and like we have some form of s, like this is like some x and this is some y, and there's like you can, and this x to the power d minus n, these are like goes like omega to the power d minus n. So like and similarly this y beta minus m is goes like omega to the power beta minus m, and this is pure gravity part, and this is like when it only appears when you couple gravity with matter. Now the point is like the leading term goes like omega to the power d, that you can see here, but there are also sub-leading terms here. You can like recursively calculate these things. And this z, which is multiplied with this universal factor, this obeys some like simple Weyl transformation equation, because this omega is now like this is, you can interpret as like Weyl transformation thing. And one thing is that here we are doing kind of some asymptotic quantization. So the details of this theory, like what other interaction we are putting in here, that does not affect the form of S here. That's very important for our case. So that may be like effect, that may take like will be like there if we go to a finite time limit, but for like this large volume limit, we don't get any contribution from these interaction terms. So now, okay. Now what is this j? Now when we find this Hamiltonian momentum constant action on this j, we find like this is already some diffeomorphism invariance, and this j is actually like as j is also follows some like some Weyl transformation properties, like some simple Weyl transformation properties, and these ads are like some anomaly terms, and we find like this j shares the same property as a CFT partition function. Like if you have a CFT partition function, which has a like source chi turned on for an operator phi with some like dual dimension, and you can find like this j over the same kind of this these relations like in equation 13, the diffeomorphism invariance and Weyl transformation. We can make it more manifest first before doing that. So up to this time, like we were on this sphere. Now we do a Weyl transformation because everything is like some different Weyl invariant kind of here. So we can make a Weyl transformation here to go this was our physical metric here. And we went to a like flat coordinate with some like Weyl we observed this factor with some Weyl transformation. This is kind of like we are doing a stereographic projection. And after doing this, we can expand j in the part in the powers of kappa. Kappa is like 8 pi gn is our Newton constant. So up to this point, there is no expansion over kappa. We are doing some perturbation about large omega. Now we are doing like for the jet part only, we are doing some expansion over kappa. And you can and this g, this curly g, these are like some multilinear functionals, which are like here you can see like there's some h insertion, there's some chi insertion, and there is some coefficient function g. Okay, yeah. So and you can see like this this different Weyl invariance they put some constant on this coefficient functions here. This coefficient function, they obey some word identities. So though this looks, the word identity looks very complicated, but just see the highlighted part. See like this trace and this divergence of n+1 coefficient is completely determined by the nth coefficient. So that's the word identity gives us here. And also this conformal word identity we can get from here, which is a particular combination of diffeomorphism and OL transformation. And this only relates, this only imposes some constant on a single this coefficient. It does not relate with some n to n+1. And with this word identity, we can like go to the finite version of this transformation, and we can really identify this G is actually some connected CFT correlation function. So, okay, so now this is our proposal. We are saying like if you supply some G which satisfy these word identities, then we can then with this G we can find a valid solution for this Wheeler-DeWitt equation. This is our proposal. You give me some G, so I will put it here in this curly G, and this is a valid state. So in this sense, we are saying like this Hilbert space is actually equivalent to a theory space, and we can also comment about the relation with the Hartle-Hawking states. So these different Hartle-Hawking states are like different states of this space only, and like for it, like if you have some L bulk, you can get some psi 0, some L tilde bulk, you can get some psi tilde 0, and both psi 0 and psi tilde 0, they are like these states for both of the bulk theory. So like yeah. So now also we do a like we go to another basis which is called like the basis of small fluctuations. We name it. So this is just a simple trick we use. Like if there is some like some this curly G and there are some curly G G but tilde. Yeah, I will just take it. Yeah. Then this particular combination, they also satisfy the word identities with this and this particular combination is necessary to like have the perfect the correct anomaly term. And now we can see like if you put this here, so this psi lambda, this also satisfy your Wheeler-DeWitt equation asymptotically, and you can take the derivative with lambda here, and that will give this particular combination which will be useful in our calculation later. This is like, so you can think like this delta G is like difference between two G's. So this is also a valid state in our theory. Now, yeah, just last comment. Now, do we get the Higuchi state that Higuchi proposed from our calculations? We said yes. Now, to do that, so we use we use this G curly G NM and this G tilde NM, and which differ for some particular m equal to m0 and n equal to n0, but that coincides for all lower point functions. And you see for the all lower point functions, so this difference it is just 0. It only starts contributing when this particular value is reached, and then we divide by kappa to the, see this n is actually like the coefficient of this how many graviton you are inserting. So so you can divide by kappa to the power n0 and take kappa equal to 0 limit. Then you can extract out one single this delta n0 m0, and that is we are defining as this is some non-gravitational wave functional. And we see like this is actually de Sitter isometry invariant that Higuchi already showed in his calculation. We get some very simple form here, and this is de Sitter isometry invariant because this delta G here, they obey this conformal word identities. Okay, and we can also go back to the seed state, though we don't need to go, but we can go back to the seed state by like undo this group averaging by fixing 3 points here. So this is this. Yeah, I'll just take last 1 minute. So here's a quick summary of what we did here. So we expanded Hamiltonian momentum constant in large volume limit, and the solution takes form of a universal phase factor e to the power is multiplied with another factor z, which we interpret as CFT partition function. And there's a quotation in CFT because when you are saying the CFT, it is not really CFT because this delta G, they have some word identities only. But we also find this CFT has like some like imaginary central charge. So this may be some non-unitary, some non-local CFT. We don't know, but just it is a very generalized CFT, you can say. And the specification of all the CFT theories is specify the quantum gravity Hilbert space. And in short, like we generalized Higuchi's construction. In this case, when kappa equal to non-zero, like fully gravitational case, we have generalized what will be the quantum gravity invariant states. And what's next? So this how we can we say the title of the talk was the Hilbert space, but Hilbert space is incomplete until you define a norm. So we can define the norm here, we already defined, and we can comment about the cosmological correlator in our setup. And we can also find the holography in this setup. And to find all these answers, please follow Tuni's talk. Thank you. Yeah.
Let's thank Priyadarshi for his talk. Any quick questions?
Yeah, so I'm a bit confused about the statement that if you can take a wave function of one theory, you can use it as a wave function of another theory.
No, it is the Hartle-Hawking state, because this wave functional, they have the same the coefficient functions which obey the word identities.
Yeah, I mean, let me just maybe phrase this question this way. What is the thing that actually tells me the theory dependence of your wave function? How does your, you have a CFT thing, okay? Now, for that, some word identities and so on. The word identities themselves don't depend on any couplings or anything, right?
Yeah.
So, where does the coupling information and so on and so forth go into the wave function?
So that I'm not sure about.
Okay, can I try and answer?
Okay.
Okay, so look, it's not there at infinite times. At infinite times in the Hilbert space, you don't have this information. It's like in flat space, if you go to null infinity, you'll get a Fock space. And there's no, you don't know what the bulk theory is. The coupling information would enter here if you tried to evolve this wave function back to finite times. So if you at infinite times, you just see the Hilbert space, which is universal for all theories. You don't see the coupling information. If you want to ask questions about bulk physics, then of course you would need the coupling information. But just to classify the Hilbert space, it doesn't depend on couplings.
So,
that's the
sorry, just one. I mean, I would think that, there's a spectrum would have the couplings, right? I mean, for example, if I have a QED, the far away, I'll get hydrogen atom with various states as asymptotic states. And then I would know the coupling dependence. I can measure the... Right.
So the asymptotic fields are part of that. So certainly, there is the couplings is maybe a slightly. So there's some question of what the matter content of the theory is and what the asymptotic observables are. But once you specify them, then whether you have a 5 to the 4th with 0.1 or 0.2 doesn't matter, unless you change the asymptotic states itself. So maybe, I mean, flat space is a good way to think about this, right? If I tell you the R square theory, or the R square plus R cube plus R to the 4th theory in the bulk, they all have the same spectrum because at null infinity, it's all just gravitons. So, you don't see the bulk information from you're right. I mean, there might be different asymptotic states itself. In which case, I mean, that's an input that we take, that, we know what the asymptotic fields are.
Okay.
We're running out of time, so we'll take the questions outside.